Okay, thank you very much for coming to my session. I will guide you through a short journey of race conditions, but at the beginning, some words about me. I started with C++ some time ago. Currently, I'm a programmer and development manager at Felix in Bremen, and we're doing medical devices primarily for displaying radiological images. And besides that, C++ has went in my private life as well, so I'm a blogger, editor on the ACCU website, regular speaker. I'm an active member of our user group. I'm a contributor to the STF's concurrency library and a member of the ACCU faculty. And I have a lovely wife and kids at home. Okay, I like to start the session with the quote: being wrong isn't a bad thing like they teach you in school. It's an opportunity to learn something. It's something which Feynman, the physicist, said. And so, if I make a mistake, please come to me, ask me directly or afterwards, and I'm happy to learn from you. So, why I'm here? I love programming, and I like sharing my experience to you, and I as well like to learn from you. Why are you here? Who has already used student thread? Okay, student atomic and all these other things like condition variables. Okay, writes for current code in his daily life. Okay, so this is more a session for beginners. So I do not want to scare you away, but this is not advanced, low-level, log-free programming session. Okay, something about what we do. That's how our workstation normally looks. So we make software to display mammography images for breast cancer detection.
Could you use that for one moment while I sort out your belt?
Okay, I will try it. And so what we normally get, we get the mammograms from the acquisition workstation where the women are examined for breast cancer. And what we get 4 images normally. So 2 were acquired from the top, 2 were acquired from the side. And the radiologist normally compares them to the images of the previous year to see if there's some kind of change in the tissue structure. And a normal radiologist does about 120 exams per hour. So he or she has about 30 seconds to do the examination and to evaluate, is there a problem in the breast tissue, or is it she can go home for the next 2 years? And in this context, we have, I think now for 8 years, we get 3D mammography images. And they had in the previously about this size, and the user wanted to display them in 30 frames per second. So they want to make a sweep through all the slices. And we are only allowed to do lossless compression. So because there's a fear that because of the compression, certain artifacts might be lost. And so on the other hand, for instance, JPEG 2000 does a very good compression, but it's way too slow during decompression. So we recompress the image into a proprietary format. In the initial approach, we used 2 user threads. And at big sites, we get about 620,000 slices per day. So that is a pure processing time of 9 hours. That was fine for many years, but then since last year, our customer came with a new challenge. They increased the images, just slightly. But of course, the user wanted to have the same performance as before. And we had to do something in the software so that we can gain the same display of images. Okay, some basics. Normally, reading data from two concurrent threads, just reading is absolutely no problem, and it's fine, and you can do it as long as you want. But if you, if you want to if you want to read and write more or less at the same time, you need some kind of synchronization primitives. We have acquired some of them atomic mutex, some of was memory fence, and transactional memory. Okay, transactional memory we don't have so far in the language of C++, but it might be that we get it in the future. And so if you write and read at the same time, you got undefined behavior. And I give you some examples of this. So, our very first example. You have a value of 42 and stored in this variable, and you spawn two threads. And you share this variable in those two threads, and you increment this value, and you multiply it by 2. And then at the end, you join so that you wait that both threads are terminated. So what are possible outputs? That's a question to you. Pardon? Yes, 43 is one of them, but there are more. Could you speak up a little bit louder? Every number is probably correct. 85 is correct too. Yes, 2. Pardon? Yes, that's true, but you can run this program on your machine. And on my machine, I got 4 results. Yes?
It's important that if it's undefined behavior because you have race conditions, then just because your machine gives 4 results doesn't mean somebody else's won't.
That's true. That's absolutely true. Yeah, that's true. I just want to give you an impression what you can have. So these were the results on my machine. Okay, we don't want this. Okay, why do we have this? Normally we have this simplified impression of our CPU. For instance, one CPU has several cores, and bigger machines have more than one core, and all they talk to the RAM. But this is a very, very simplified view of what's actually happening. In reality, we have something like this. So we have several cores, and we have level 1 cache, level 2 cache, level 3 cache, and then the RAM. And as soon as one starts changing here one value, this change must be propagated through all the caches and even on the other chip too. Okay? So now we change here from undefined behavior to defined behavior. So we start again, we store the value in an atomic. Just a second. Okay. And we do exactly the same. We increment the value and multiply it by 2. We join. So what are now the possible results? What do you think? No, not exactly. Sorry. Not exactly. So, so we have 84, 85, and 86. These are possible results. Does everybody understand why we have these different results? If not, please ask. Okay. So we can do literally the same with the mutex. So this mutex shall guard the int value, and we use the unique lock within the thread on both sides, and we join. What's now the result? What are possible results? Yes?
85.
Yes, and?
86.
Correct. Okay, so this is basic. So next thing is beware of your compiler. Sometimes he's doing something what you're not expecting. So we have a very simple program. We have two variables, x and y, and we assign x to test. We have a function which set y to test, and we spawn this function in a thread. Yeah, and then we wait until test is 0. We wait as long as the test is 0, and then the application should join. What is happening here? Or what might happen? Pardon? Could you speak up a little bit? Yes, the program will never stop. Or it can happen that it never stops. Because there's an example, or this example I got bought as well, that you can look into the assembly. What is happening? Test is not an atomic. So at this point, the access to test is not synchronized. And since test is not synchronized, the compiler can assume that test is just changed by the main thread. So it optimizes its away. The compiler is allowed to do this because you are using, or in this program, you're using undefined behavior. And the compiler tends to optimize against or on undefined behavior very much. So even if you think it's just an int, and it, of course, the write to an int itself is one operation. So the machine itself will not write one bit after the other one. So all 32 bits or 64 bits are written at one step. But even in this case, or even these access must be synchronized. That's very, very important. Okay, let's come to our domain problem. So the problem was that we want to compress the images faster, as we did it before. So what we do, we take, oops. Yeah. So we take the image and we divide it in a number of stripes. And each of the stripes shall be compressed in a single thread, so that there's no need to synchronize, because synchronizing stops or blocks. So, each of these small stripes is then compressed, and we bring everything together in such a smaller image with compressed stripes into it. And then we store them on the disk, and later on we can decompress everything in the same manner. So we just decompress small stripes, and this can be parallelized very easily. So that's the goal, what we want to achieve. So the original routine is, of course, much bigger, and I reduced everything to this minimal example. So we have something which I call a compressed context. There is it has information about source image and where the target pixels shall be put. Then we have one function to compress this stripe, and later on we have one function to merge all stripes together into one final image. So in our initial approach, we used 2 user threads. So we create a vector of threads, and we in each thread this compression function should work. So, and at the end, we join, so we wait until every slice is finally compressed, and we merge everything, and then we're done. Okay? If there's any question, please do not wait until the very end, but interrupt me immediately, please. So, problems with user threads. User threads are very, very expensive. And we had measurements on our machine that it could happen that spawning a user thread could take until 1 second. Perhaps this is a problem more on the Windows domain, but since I don't know how this is on Linux, but it can be very, very expensive, especially if you spawn many, many threads in very, very short time period. And another problem is if you start more user threads than you have cores, then you start doing oversubscription. So then your handling of all the different threads slows you down because each context change, or on each context change, the CPU has to store many, many information so that it can later on continue the thread. So we came up with the idea to use thread pool. Who is not familiar with the concept of a thread pool? Okay, a thread pool is a machine which is hopefully provided by your operating system, and you just give it a task, so that's a function with no return value, and you just put it to the thread pool, and whenever the next slot is available, it does the computation. And normally it has more or less the number of threads as you have a course, and it automatically uses the core as efficiently as it's possible. Okay? There are several ways, or I often read questions, how do I implement my own thread pool? I would advise not to implement your own thread pool. Use something that is ready-made, because implementing a thread pool that is slow, that's very, very easy. But to implement a thread pool that is highly efficient, it's a job or a task on its own. It's an own project. And for instance, Windows has its own thread pool. Then on macOS, there's libdispatch, which is, I think, available on Linux as well. And for Linux, I think there are implementations available as well. So what I used so far here is the thread pool abstraction, which is in our library. But you can easily exchange this with your own thread pool implementation. So what you do, you pass, at this point, just a lambda to this executor, and whenever it's ready, or when it has an available slot, it just executes the task, and then you're done. So at this point, we, okay, yeah. And within this task, we do the compression of the stripe. So, but in this case, we have to signal somehow that we are done, so that all tasks, that all stripes were compressed. So for this, we use an atomic counter, and we decrement it whenever one stripe was compressed, and we are done. So, and we loop until we are done. But how we then, yes?
I have a question regarding default executor.
Yes.
This is the only way to verify that it's finished?
The question was, is there a way that the task is finished? No. You have to do this by yourself. That's the way as I do it with this atomic counter. So that all the thread pools work normally. So you just can pass a void function to it, and it's calculated, or it's processed, and then it's done. And then the task is removed from the pool. So if you want to have some kind of notification when this task has finished, you have to do this by your own. And and that's the way I'm using here this atomic counter. So I decrement for each stripe that has successfully compressed. And then when all stripes are compressed, then we're done. But we have to block, at this point, the main loop so that it does not continue. So, and for this, we use this unique lock in combination with a condition variable. So, who is not familiar with the functionality of a condition variable? Okay. When the program comes to this point, it acquires the lock on this mutex. And since we are not on, since we are at the very beginning, to do is unequal 0, and then we stop here on this condition variable. And it releases the lock, and it blocks this current thread until it is woken up. And that is happening here now in our loop. So when we have compressed a single slice, we decrement, and then we tell the condition variable notify 1, so wake up the main thread, and then it can proceed. And we do this, we have to do it as often as there's some work left to do. Yes?
This happens to be an interview question for me, so I just thought I'd share with people. The while paren thing is an idiom. It's not something you would think to do. You would normally say if, but the while is an idiom because it can not happen. You need to keep going so you don't get race conditions. So if you do the if wait, and then it's okay, by the time you're done, it might not be okay. So you might want to say that that's an idiom, the while.
Yes. Yes, and John pointed me correctly to that this while something until the final condition is not reached, and then stop on fall into the wait. That's the typical idiom, and you have to use this idiom because it can happen that this thread is called spuriously woken up. So this has something to do with the hardware architecture below. So it might happen that it gets woken up, and at this point you have to recheck, is my final condition really reached? So it might happen that you are falling here through, even that we are not notified. That can happen. Yes?
Is this atomic means necessary to check?
In this way, as the code is written at the moment, yes, it must be an atomic, because the to-do is not guarded by a mutex. Okay? Yeah.
I think that in this case, the modification of the condition has to be protected by the mutex, because if it's not, there is an opportunity for the wake-up signal, the notification signal to be lost in this case.
Just a second. That's the reason for my talk. It's an adventure. So we pass through quite a number of problems you can arise, but you already saw one. Yeah.
Is that random waking up to do with random priority inversion in Windows?
I think it had nothing to do with Windows. It's a general thing on the CPUs. Otherwise, if they would prevent this, as I understood it from the documentation, if it would be guaranteed that there's no spurious wake up, that would be a slowdown in most of the cases. So, okay? Okay, so we begin with our adventure. So in this case, we had a problem. The real application did not terminate. Do you have any idea why? Yes? Not exactly. The point is something I didn't knew until I fell into this trap. Even a shared, it's a quote from CPP reference. Even a shared variable is atomic. It must be modified under the mutex in order to get correctly published to the waiting thread. Okay? So, I think that's pretty easy to fix. It's a reference to CPP reference on this. And we take this one and change it to this one. Okay? Problem solved. I see that you take many pictures. Of course, you can take them, but all the slides will be later available. So it's, for those, easy. Okay. Done.
Question?
Yes?
Does to do it need to be atomic?
No, at this point, there's no reason to be atomic anymore. That's true. So, then, but we ran into the second problem. At this point, the application crashed. Do you have an idea? Okay. Try to give you this picture and to visualize what was happening here. So this is the code from the main thread and the things which were interesting. So in thread 1, we went, the thread 1 did the decrement. In the second thread, we did a little bit later a decrement as well. So then, from this thread, the notification for the main thread happened. So we proceed here. And at this point, when we leave here, the condition variable is destroyed. And then here we have a nice crash. Okay? Okay, we do the next fix. So what we do, we move this up. Yes?
But the problem in the previous one, which was correct code, was that we didn't join the threads correctly. That was the only problem. It's not a problem with that particular code. It was a problem that we didn't join the threads. We should have joined the threads before exiting main. Before destroying the condition variable.
Yes, okay, but this is, at that point we come to a problem of, nothing is for free. That is a problem of the thread pools.
Yes.
So,
The thread pools should have been
yes.
properly destroyed before exiting. Because that fix it would work, but it's inefficient.
I see your point, but on the other hand, we have this discussion with some users in our library as well. And, but in general, we don't want to add this extra complexity to the thread pool because this is a cost which you have to pay most of the time. So what we have to do is some kind of ref counting to the tasks that you publish to the thread pool. And this is, in general, we try to avoid. So we don't want to have this extra cost because we use this especially for high performance stuff. So if you have the problem that you come into, so that you can, in the situation that you still have tasks on your thread pool, but it may be that your application is terminated or is ended, then you have to take care of this. But you have to take it for yourself in advance. Yes?
Experience from this is that it's impossible if you don't have some deterministic distraction point where you stop and you join all your threads before leaving main. There are a million bugs that appear. There are a million opportunities for crashes because your object is essentially, especially if you use pointers, that threads are using and so
Yes.
on. If
So-
they get destroyed from different threads, there are opportunities for like a million
Yes,
attacks.
yes, you're absolutely true that there are many opportunities to get into problem here. If you use standard threads from the C++ library, then you don't have the problem because they all of them block until the task is fulfilled. So there you don't have the problem. But if you start using thread pools, then you have to take care of this problem. Okay, more questions? Yes.
That second set of curly braces, lines 10 and 14, are they all necessary now that everything is...
No, they are not really necessary. They're just for illustration purpose, because this is another typical idiom that you put these guards into as close scope as possible.
just to show their context?
Yes. Normally, in this case, you're right, the curly braces are not necessary. Okay. Then we wanted to add some kind of error handling, because it can happen that that's a problem of this compression algorithm, that on certain image pattern, it could happen that the compressed image is larger than the original image. And this is a failure that we wanted to detect. So in this case, it does not make sense to store a bigger image than the original one. In this case, we wanted to have at least just the size of the original one. So we added some kind of error handling. In this case, if the compression is successful, we return true, otherwise false. And for this, we add an atomic bool which shall handle the abort case. Just move up a little bit of the code. So if we come in the task and we see that the complete compression was aborted because another slice already signaled we shall not proceed, then we immediately return. If we can proceed, then we just remember locally that the compression, if we shall abort or not, and we remember, shall we abort to the outside? Okay, and then we, while as long as we have something to do and we did not and shall not abort. Clear so far, or have questions? Yes?
So why don't you leave another notify one on line 9? How would you not add to?
It's a good question. One should do, yes. Thanks for noting. Okay, that's the same, but we have another race. We have another problem. Do you see the problem? Okay, I give the conclusion. So, none of these variables exists when there's an early termination. So we have the same problem as before. So we have an early exit, then we must not use any of these variables in the other threads anymore. So, for instance, if the very first task detects, well, I have to terminate the application, or I have to terminate this compression, so then it aborts, and then we fall through the while. And then we destruct all the local members that we have above, and we have the same problem as we had it before. Okay. Okay, what's the way to fix this problem? So we put all these things into what I call a process context. So, so we take the mutex, the condition variable, the to-do, which is only an int is needed, and the atomic bool into a structure. And we create a shared pointer of this structure, and we pass it as a weak pointer into our task. So into the task what we want to, or that we push to the thread pool. Everybody clear why I create a weak pointer? Who wants, or who doesn't know why I use a weak pointer here? Okay, the weak pointer has the advantage at this point. So, so whenever one of these tasks terminates, then it, as we have seen, it can fall out of scope, and then it would delete our process context. And it should delete this. But as soon as we are inside our task, we want to guarantee that it's not destructed. Okay? And this can be achieved with this, I don't know if this is a pattern, but it's a way as we do it very often. So we create, of this shared pointer, we create a weak pointer, and inside the task, whenever it started, we take the lock on this weak pointer, so we get the shared pointer back. And if this shared pointer exists, and we did not abort so far, then we can proceed. And the rest is just as before, just dereferencing the context in all the members as before. And then we are safe in all cases. Good. Conclusion. Just picture of the a new CPU that I just bought for my own machine. It's very nice to have many cores, and it's very cheap to get many cores today. I think Intel just announced they have a 56-core CPU available quite soon. So it's quite easy to get a CPU with many cores, so to distribute all your work in smaller tasks onto these machines. But it's, from my experience, it's very hard to write concurrent code that is fast and correct. If one uses low-level synchronization primitives, so that's mutex, atomics, and all these other, it's very difficult to write it correctly. And I highly recommend to use always high-level abstractions, for instance, like futures, or channels, or actors. There are several libraries out there, and they make your life much easier. And you don't have to try to optimize this because mutex have the problem of synchronization, and you can easily run into deadlocks and all this stuff. So I really highly recommend to use this. And just to give you a small glimpse of how one could do this, for instance, with Boost. Boost has some features. You see, most of the code is just boilerplate. So the actual code is just here below, and it does the same as all the slides before. It has exactly the same functionality. So we just create a vector of Boost futures. We create async tasks, as many as we want. And then we pass all these tasks or this range of tasks to when all, and this continues. When all tasks are fulfilled, then it continues and executes this. So that's what we call a continuation. Yes?
But we have to call done.get at the end, right? Because this program will exit and it will not do anything, right, at the end. So we have to get the value from done. We have to call done.get.
Not in this point, not at this, because merge does not return a value.
Yeah.
But so,
Even void, because does boost future call get on its destructor? So will it block main at this point?
yes,
Because STD futures don't do it.
STD futures does it as well. Well, STD futures, yes, they block on destruction as well. That's a problem of standard futures and boost futures.
They don't block, actually, async futures return from async block in STD. Other futures that are not returned by async do not block.
He agrees, then it's probably, yeah. So I don't have much experiments with stud future and boost futures because they have a bunch of other problems. And therefore we use our own library, which don't have these problems. And if you are more interested in this, later on I have a reference section with several papers and videos regarding exactly this problem. This was my talk from last year, where I listed all the problems that you have with the current stud futures and boost futures. And there's a proposal on the way to fix all these problems, but it seems that this will not make C++20, but probably C++23. Because before all this future can be solved, the executor must be solved, or executor must be finalized. And they are needed, I think, for ACCU as well. And so when we have the executors, then we can get usable futures as well. But this is 23, I think. Okay, when I say our futures, that's the concurrency library inside the ST lab. It's a library which is originally designed by Sean Parent, and I joined as collaborator to this library. And we provide futures and we provide channels and other useful abstractions in regard of concurrency. It's quite similar here. One creates a vector of futures, one creates other tasks and passes them into this vector, and then we join on all futures that were passed. And as a continuation, we have at least here a merge again. And here's a difference to the standard. Here it's necessary that one calls a blocking get, otherwise this will immediately terminate. Okay, so and this, I think it's much, much easier. It's easier to read, and it's easier to reason about, and it's much, much harder to make errors on this side. So I really can highly recommend, don't try to implement your own synchronization primitives if you don't really have to. If you're doing low latency trading or something like this, and you are really up to the latest nanoseconds, and these are important for you, then of course you have to go into this taking care of atomics and all this stuff. But I really recommend don't do it. You make your life much easier and the life of your colleagues easier. Especially it's much easier to show or to prove is a strong word, it's from the mathematical side, but it's easier to demonstrate that the code is correct. If you have implementation with atomics and mutex, it's very hard to really be sure that your implementation is correct, because it sometimes works runs on different machines with different on a different architecture, for instance, with much more cores, or suddenly with much less cores, and it's really hard to test that this kind of code really works correctly. And if you use high-level abstraction, then it's much easier and to understand. So here one can really read, when all these things is done, then do this. Okay. Good. Good. I did some measurements because we wanted to improve our performance. This graph shows two kind of calculations. In blue, we see the calculations of a slice on user threads, the other one on a thread pool. So overall, we got the improvement by increasing the number of stripes. So you remember, initially we just divided the complete image in 2 stripes, and this would be this point. And then we increased the number of stripes so that we parallelized the work to be done, and then we could push down the processing time. And you see, any guess how many cores the machine had when it did these measurements? Pardon? No? 4. That's correct. One sees it at the blue line. Here's when you start using user threads, it's the minimum. And then it starts at the beginning slowly, but then it's going up faster. So if I divide it if I start 64 user threads, I'm getting slower again because of the oversubscription on the CPU. And there's another, I think, very interesting thing. The variation of calculations. So if I use the thread pool, it's more or less in this range. So I think, I don't know, remember, but I think I did several thousands calculations to get good statistics. So I'm always in this kind of range of calculation when I work on the thread pool. When I do it with user threads, I have this huge amount of variations. So this is the maximum time it really took to process this image. Okay? And this is the same with the little bit bigger image. So this is the original sized image. And here we see, again, the same, that the variation using a thread pool, it's much slower than using user threads. Can someone explain why there's, in the end, in the overall, not that big improvement between, or why is that the difference is not that big in the middle between the user threads and the thread pool? Yes?
I'm going to guess that the data set size is big enough that the working set of the machine is too large.
Yes.
And this seems to happen a lot with big problems, and people do micro benchmarks with little problems. They don't understand this.
Yes, you're absolutely right. So he said that the problem is in the huge size of the image. So at this point, we come to the images are so huge that they don't fit in any cache. So what we see here is that the memory bandwidth from the cache from the CPU. From the memory to the CPU and back to the memory, it's a limiting factor at this point. So we cannot get fast enough the pixel data from the main memory onto the CPU, do the calculation, do the compression, and then put it back. Okay? Yes?
I have a question. So why would you not segment your problems so that you work on whatever you need to work on at the appropriate working set size, but not exceed it, and then just simply do that serially? Because you should be able to get, however many cores you have, you should be able to get that kind of speed up, no?
What do you imagine how to? Okay, I forgot to say something about how the system is structured. So we receive the images via TCP on a server. There we do the recompression, so we decompress them from JPEG 2000 into our format, and then we push the images to all the clients, which is up to 20 in a clinic. So, so there is no, I think there's no other way to, we have to transfer the compressed image in one bunch to the client. So we don't do any kind of streaming because the hospital network is often not that fast enough to support some kind of streaming. So so what we do, we overnight, the images are sent to the system, all this pre-processing is done, and then they're transferred to the clients. And so the client just have to read the compressed images from the disk to the memory, and then to the display.
So what is the bottleneck where you need to have the entire picture in core and process it globally? What is that compared to taking the image? If you have stripes,
Yes.
you can, when the image comes in, whatever it is, you can break it into as fine stripes as you want, right?
That's what we're doing.
Okay.
So
Is that this picture or the next picture? This picture doesn't show as big a speed up because it's the whole picture, right?
yes.
Okay. So could you not do this? Could you not take the big picture and break it into as many stripes, so segment the problem into n problems of size that fits in the working set, and then distribute that across your 4 cores, getting a 4x speed up over what you're doing now?
I think we're doing this. At the beginning, we just had 2 stripes, but now we reduced. We make stripes much thinner, and we're doing. I think at the moment up to 16, but it's configurable. If the machine have more cores, you can.
So there was another picture that you had right where the speed up wasn't as good, right? Because you had the bigger picture.
Yes.
Why is that? So is your fix to then cut the problem down to so that the working set size is all the memory you have, and then divide that across the 4 cores?
So what we do is we now distribute it to 16 or as many cores as the machine has, because at this point we use a thread pool. So it does. We know the machines which are in the hospitals, and currently they don't have more than 12 or 6 cores. So, and since we are already doing in 16 stripes, so we are doing it's smaller as is necessary.
So this is, go ahead,
Yes.
and say what I'm saying.
So it sounds like it's suggesting that you break the image into stripes that are smaller than the L1 cache of the processor, not into the number of...
Exactly. That's exactly right. So, do you understand what?
I think I understand. So internally, it works line by line.
Yes, cache lines.
No, image by image line.
Okay.
Yes. So internally, it just compresses a single line, and then it does the next one. Yeah.
So you have a very fine granularity. You could split this into 1,000 problems if you wanted to.
Yes.
Right, perfect. Now, what I think you're doing right now, and correct me if I'm wrong, is you're splitting it so that the size of the stripe fits in L1 cache. Is that true?
No.
No. Okay.
I see your point, and I think it's a good idea, and I will
want to do
take it
better
back.
than that. I want a size of the stripe to fit in a quarter of L1 cache, so you can get 4 processors on it. Or I want a size of the stripe to fit eight of them in there, so you can get 8 processors on it.
Yes.
And still get the memory, because you can split it into such a small problem.
Yes.
I believe you can get a factor 4 speed up, and I believe this is an eminently parallelizable problem.
Yes, and I understand you. But the situation is a little bit more complicated because we would get the best performance if the server and the client have the same CPU architecture. So if the sizes on the caches on both machines is the same, but it's not. So,
Okay, how about this? How about
so
this?
I know what you
So take the smaller one.
yeah.
That's fine. So whatever cache you're aiming for, it might not be L1, it might be L2. Whatever one you're aiming for, because there's a size that matches the cache.
Yep.
Find that size, and then find how many processors you have, and take the minimum on both ones, right? And then you'll have enough memory. You won't thrash on any process. And of course, you have to worry about fault sharing or most fun things. But I mean, you know, this is
I-
not a problem.
I understand.
But you can do it. I know you can.
Yes, that's a good idea. Yes, thank you.
Problem with that is, when you're compressing an image line, don't you need additional lines to do that compression? And assuming so, if why don't you split it, more overhead of lines need for the calculation, which you didn't need
Yes, I think
in the answer.
you're right, but I think
Why don't you split it with the
yes, but this must be taken into account. How many pixels on the lines below, above and below are necessary.
Don't listen to the guy in the back. I see where's you.
I do not work for the guys of last Saturday.
Oh, shoot. He's right, of course. But here's the interesting thing. We've been doing a lot of benchmarks that he doesn't know about, so I'm going to tell him later. But the bottom line is, if you imagine that you do powers of 2 to measure this, to benchmark this, let's assume you get to within 1/2 of the size of your cache. All the overhead that you're using is the extra memory fits in that extra, we'll just call that garbage. So if your cache is, let's say, 2 to the 18th bytes, when you get to 2 to the 17th as your data set, the other part is the leftover stuff. You want to make sure that the size that you size it to is half the size of whatever working set size you want for how, divided by however many processes you have.
Yeah, I understand what you mean. I will check it at home.
Will you get back to me? Because I bet you can get a factor 4 improvement.
I will try it
Okay.
at home.
Can I sell you now?
I think I was in your session last year.
But you should come to mine on Saturday this year. That is a plug. Because I will tell you some stuff.
Okay, great. I think that's what I wanted to see. So again, a strategy. Try to break down your problem into small parts, that as we just discussed, and try to solve it without the need to do any kind of synchronization. Because any kind of synchronization blocks and slows you down. You just have to keep Amdahl's law in mind. So and it kicks you very early, very hard. Use high-level abstractions. I cannot repeat it enough. It makes your life much, much harder. And try to think in parallel. That's very hard. You have to keep in mind that any operation can be interrupted at any time. So it can happen if you read your C++ code or Java code or whatever, it can happen between each and every line. It can happen within a line. And it can happen as well in parts that you don't see. For instance, synthesized constructors, destructors, and all this stuff. At this point, everywhere, the scheduler of an operating system can kick in and say, well, this thread is over, and now it goes to the next one. You go first.
So you see it a lot in embedded where you don't have single operation read writes, so you can't lock a mutate, or you can't create a lock for easily because you can't read a boolean and write it in the same operation. So you can read it, something else will come in and interrupt it at that point when you're reading it, both read to write it.
Okay, sorry. It was a little bit fast to repeat.
So if you've got an if,
Yes.
if locked, then, or if not locked, then lock type operation, because you can't do that in one processor cycle in some embedded system. You can get it where 2 threads both at the same time try and lock it.
Okay. So you said that on embedded system you get in problems where certain operations cannot happen at the same time. And this makes thing much more fun.
There's an example in
x86, where even the increment of an int, which is a single instruction, will be able to conflict with itself rather than a second tab. Which means that the instruction itself is not even atomic.
Yeah. So, so some acknowledgement, my family, which support me when I'm working in the evening on the concurrency library. Sean Parent, who is great and taught me lots of stuff and gave me permission to whatever I used, what I want to use for my company. Give me time to be here. C++ user group, which is my guinea pig for all my sessions. And all the other contributors to the concurrency lab. I have some kind of reference if you're interested in reading more. That's our library, the documentation, a great book, which is a classic from, I think, 79, 76, communicating sequential processes. It's public domain, or it's at least available online. Other publications, a proposal that David Senkel, Sean Parent, and I did on the futures. And there's already talked about. This is a new unified proposal for futures by Bryce. And further reading, I think it's always good to read those two books, Elements of Programming, and the other one from Alexander Stepanov and Daniel Rose. Some other frameworks and things to look at the HPX framework, another CSP library, an actor framework, and Anthony Williams' second edition book on concurrence in action. But this is more, I think, more low-level book than a high-level abstraction book from my experience, but other might see it's different. You can read and view more. And for those who are interested in how thread pools work, there's a great video by Pedro Teixeira at Microsoft, how they implemented the Windows thread pool. It's perhaps not really up to date because it's already some years ago, but it shows lots of the problems that you can face and that why you should not implement your own thread pool. Okay, this is our library. You're welcome. If you have questions or so on, thank you for your attention. Questions more.